Good morning everyone. Today we are going to see robust RBFN, that is robust radial basis function network. So, what is a robust radial basis function network? An RBFN is a type of artificial neural network that uses radial basis functions as its activation functions that is present in its hidden layer. It is having only one hidden layer and hence it is a simplified neural network that can be useful for approximating nonlinear functions. In general, RBFN consists of an input layer, a single hidden layer where the radial basis functions are applied, and an output layer that provides the final prediction or the classification that is required. Now, coming to the structure, as I mentioned, it is having the input layer, hidden layer and the output layer. The Gaussian function is the most commonly used RBF radial basis function, that is defined as phi of x equal to exponential of minus norm of x minus center whole square divided by 2 sigma square, where x is the given input vector and c is the center vector associated with each of the hidden layers or hidden neurons, and sigma is the spread of the Gaussian function. And other RBF radial basis functions are multi-quadratic, which is given by phi of x equal to root of x minus c norm square plus beta square, and inverse multi-quadratic, which is given by phi of x equal to 1 by root of x minus c norm square plus beta square, where beta in this multi-quadratic and inverse multi-quadratic functions is nothing but a parameter that affects the shape of the function. Such a network can be represented as follows, which is given by f of x equal to summation over I equal to 1 to r wi phi I of norm of input minus the center mu I comma theta I, where x belongs to n dimensional Euclidean space is the input vector, phi I is the basis function of the network, and wi's are the weight vectors connecting the hidden layer to the output layer, and mu I is called the center vector of the ith node, and theta I equal to theta I1, theta I2 up to theta In transpose is called the bandwidth vector of the ith node. And here is the architecture where we have only one hidden layer and we have an input layer and an output layer, and hence it is a simplified one and can be used as a good function approximator. Now, coming to the training at RBFN. So, training can be done simply by pseudo inverse technique, or it can be done by back propagation method. So, first step in training is determine the centers. Centers can be determined using any cluster algorithm such as k-means, and these centers are crucial as they define where the radial basis functions are centered, and compute the spread. The spread of the radial basis function sigma can be determined based on the distance between the centers. Common approach to find the sigma is the average distance between the centers. Now, final step 3. The step 3 is optimize the weights. The weights connecting the hidden layers to the output layer are optimized using methods such as linear regression or gradient descent method. The goal is to minimize the error between the predicted output of the network and the actual desired output given to the network. Now, coming to the major topic, function approximation. The process of estimating a function that best fits a set of data points is called function approximation, and it is used in various applications like prediction, interpolation and data smoothing. There are two main methods to do this function approximation. One is parametric and another one is non-parametric. Now, let us see the first method, which is called parametric method. Parametric method assumes that the relationship between inputs and output can be described by a predetermined mathematical model. Thus, the task is to find the optimal parameters for this model. Example is linear regression, models relation between the input and the output as a straight line, We assume that the function is of the form y equal to beta naught plus b1 beta 1 x, and we have to find the parameters beta naught and beta 1 associated with this function. Advantages for this parametric method includes simple to implement and interpret and computationally efficient, whereas the disadvantages are assumes a specific form of the function and it has limited flexibility. Now, coming to the non-parametric method, these methods do not start with a predefined formula. Instead, they learn the relationship directly from the data, which is advantageous for handling real world data. That data exhibits really non-linear relationships and it also exhibits complex relationships. Example for this method is k nearest neighbors, which predicts the value of a new data point based on the values of the k closest points from the training set. And advantages for this non-parametric approach includes highly flexible and capable of capturing intricate relationships within the data, and it does not rely on the specific functional form as in the case of parametric method. And the disadvantages is it is computationally expensive and it requires a substantial amount of data in order to achieve a better performance. Now, let us see mainly on function approximation using RBFN. The radial basis function neural networks are a good candidate for function approximation because of its faster learning capability, because it has a simplest architecture as compared to multi-layer neural network. For function approximation, traditionally we use RBFN with Gaussian functions as the transfer functions and the method of least squares. This methodology works most of the time, but there are certain bottlenecks associated with using Gaussian functions directly as the activation functions. That include difficulty in the methods involving constant functions and the impact of outliers. These are the two bottlenecks associated with RBFN using Gaussian function as its activation function. First, let us see what is the difficulty associated with the constant functions. When the target function remains nearly constant in certain regions, a Gaussian function struggles to approximate that constant curve effectively without using a very large bandwidth, and this can lead to inefficiency of the network performance. And also there is an impact of outliers. When the training data includes outliers, which means the value significantly different from the majority, the network's response in those regions is often inadequate due to the limitations of the least squares method. And you can see the results that has been taken from the work of Chin-Cheng Lee in the year 1999. They have proposed this RBFN based approach for function approximation specifically, because we are going to see RBFN for function approximation in the first phase of this lecture, and in the second phase we are going to see how it can be utilized to control a single link manipulator. So, here we can see the first figure, it is basically the result of approximating a piecewise constant function, and the solid line is the desired one and the dotted line is basically the network output. Similarly, figure B shows a poor approximation, that is between the solid line and the network output, and you can see that in the second case we have outliers significantly visible and it shows the performance is not very good in this function approximation. So, the solution here, when we want to use the RBFN in order to have the functions that is constant in some regions and also having outliers, we may go for robust RBFN to tackle these two bottlenecks. We can make the RBFN robust by involving, instead of Gaussian activation function, a composite of a set of sigmoidal functions can be used, which aims at approximating a given function with nearly constant values. Use a method from robust statistics to reduce the impact of outliers. Then the first one, in order to address the constant layers of the functions, we may use a combination of sigmoidal functions. Second one is, in order to address the effect of outliers, we can go for a method called Hampel's M estimator, which is efficient in handling large errors. Now, coming to the construction of a new activation function in one dimension, we are now familiar with the sigmoidal function, which is given by 1 plus e power minus bx, where b is greater than 0, that is the common sigmoidal function. And for obtaining a radial basis function, we combine two sigmoidal functions as follows, given by g of x here. G of x equal to 1 by 1 plus e power minus beta times x minus mu plus theta, minus 1 by 1 plus e power minus beta times x minus mu minus theta. The image on the next slide shows three different RBFs, radial basis functions, with the following values of the parameters, which involves mu equal to 3, beta equal to 5, 1.2 and 0.6, and theta is again a vector of 2.5, 1.5 and 0.5 respectively. For that, you have this profile for g of x with respect to mu value. Okay, so we can see that g of x for a given x can be obtained for this 3 RBFNs sigmoidal functions. So we have this performance given here. Here we can see that when either beta or theta are large, the function looks quite rectangular, which indicates that it is good for approximating constant functions. At the same time, the curves exhibits the properties of radial basis functions, so that they are valid activation functions for radial basis function neural networks. Okay. So, in higher dimensions, the proposed RBFN activation function can be defined as g of x equal to a product from j equal to 1 to n 1 upon 1 plus e power minus beta j into x j minus mu j plus theta j minus 1 upon 1 plus e power minus beta j into x j minus mu j minus theta j. Now, let us talk about robust objective function. The method of least squares is not ideal when there are some outliers in the training pattern. The reason is as follows: assume that theta is the parameter of the network, which is being adjusted each time by minimizing a given function, say E of RP. What is RP? Residual. We will be seeing that in the upcoming slides. So, the adjustable parameter theta is given for each iteration by theta k plus 1 equal to theta k minus eta times summation p equal to 1 to capital P dou E of RP upon dou theta k. Here eta is the step size parameter, you can also say learning parameter, and E of RP is the objective function, and RP is the expression that is given, residual error, that is given by desired value, target point minus target pattern corresponding network output f of xp. Generally, the objective function requires even symmetric property, that is E naught E of 0 equal to 0 and continuity, and the differential term in the above equation can be obtained as follows, which is given by summation p equal to 1 to total number of patterns. Dou E of RP upon dou theta k is given by the chain rule inclusion, dou E by dou RP into dou RP upon dou theta k, this one. That is given further by summation p equal to 1 to capital P psi of RP into dou f of xp upon dou theta k, where psi of RP is given by dou E of RP upon dou RP is called the influence function. For the acceptable performance, difference between the output of a network and the desired output given to the network should be close to 0 or must be lesser than the tolerance value for all the training patterns. But if there are no outliers, that means the errors that are very different from the rest of the data patterns, all the training data points will be accurately positioned and their residuals, that is the difference from the desired output, will be close to 0, which means RP is equal to approximately close to 0. But when the outliers are present, their large residuals significantly affect the network performance, because the network keeps adjusting its parameters to fit these outliers, which can distort the performance of the network. When outliers are present, the network struggles to accurately approximate the underlying function, because minimizing the least squares criterion alone is not sufficient. Now, to eliminate such a problem, we use M estimators, which take the general form given by summation over p equal to 1 to capital P dou p of Rp upon dou Rp is equal to 0. In this case, we specifically use Hampel's M estimator, whose influence function is given by psi of R equal to R when A greater than norm of R, A signum of R when A less than equal to R magnitude less than equal to B, and it is given by C minus R magnitude upon C minus B magnitude whole multiplied by A into signum of R when R magnitude lies between P and C range and it is 0 otherwise. Now, the following figure shows an Hampel's M estimator with A value given by 1, B being 3 and C being 4. This is the Hampel's estimator, M estimator for the given values of A, B and C. Now, by observing the previous function, we can define a class of robust objective functions for the sigmoidal RBFN of the given form. E R of Rp equal to summation over all the patterns phi of Rp minus phi of 0, where phi of Rp is a continuous function and phi of 0 is a constant and P is the total number of input patterns. Now, the derivation of psi of R influence function will take the form psi of R equal to S of R into T of R, and S of R is an odd symmetric monotonic continuous function and Tr is an even symmetric and continuous function that satisfies T of R has a unique maximum at R equal to 0 and T of R ranges between 0 and m, where m is a real number and T of R increases strictly for R varying from minus infinity to 0, and then limit R tends to plus or minus infinity S of R upon G of R is equal to 0, where G of x is given by 1 by T of x. Here, to make this objective function adjustable, we can add an adjustable parameter in either S of R or T of R. Example, S of R can be expressed as R and T of R equal to e power R square upon 2 sigma. Now, coming to the learning of the network parameters, that means a parameter update rules, we use a gradient descent method for updating the parameters, that is dou E R of Rp upon dou Wi equal to summation over all patterns dou phi of Rp upon dou Rp into dou Rp, this is chain rule, dou Rp upon dou Wi. Now, including all the parameters in a vector W, we can write the learning rule as W of t plus 1 equal to W of t plus delta W, where delta W is given by eta learning rate into dou E of Rp upon dou W. Here t is the time step and eta is the learning rate that varies from 0 to 1. Now, coming to the adaptive growing technique of the network, for a radial basis function network to perform effectively, determining the appropriate size is required, but in order to have the optimal size, it is difficult because we do not know. So, in that case we need to go for an adaptive approach which dynamically modifies the number of nodes according to the specific guidelines. Add node, delete node are the methods that we are going to follow as per the adaptability. So, add node, if the network is underperforming or learning too slowly, a new node is added at the point where the error or the residual is highest. This strategy allows the network to improve by concentrating on the areas with the most significant issues. Similarly, delete node, after several tries or iterations we remove nodes that have very small significance. These nodes do not contribute much to the learning process. So, removing them will not affect the network efficiency. Now, algorithm implementation, coming to this point, the following are the definitions of the terms associated in the algorithm. Check period T, which means this tells us how often to check the network. If the network number of iteration is a multiplier of T, we check how the network is performing. Next, the objective function ER of I. This value shows how well the network is learning during the iteration number I, and the threshold delta entropy upper, which means delta, the threshold related to the upper limit. If the difference between the current and the previous values of the objective function is higher than this threshold, it means that the network is getting better. We then reduce the range of errors. Similarly, we have another threshold towards the lower value, that is delta entropy lower. If the difference between the current and the previous values of the objective function is smaller than this threshold, it means the network does not have enough nodes to learn well. So, in that way we need to add a new node to the network. Again, threshold weight, delta weight, nodes with weight smaller than this threshold will be deleted. And finally, we have a threshold delta stop, which means to terminate the training process. With all these required determinations or definitions, we can define the algorithm as shown below. Step 1, set up the network initial conditions, select the initial number of nodes for the network, set initial parameters associated for each node, and set ES equal to epsilon to a small value where ES is used to record the value of the objective function, and set I equal to 1 and initialize the check period T. Then step 2, construct the robust objective function, which is very essential here. Select proper S of R and T of R. Compute extrema of the equation, which is y of r equal to S of r into T of r by solving the equation y prime of r equal to 0. The extrema positions represent two cutoff points. Let these be plus or minus S. Let minus S to plus S be the initial confidence level of the residual. Then compute the objective function, which is robust objective function ER of RP by integrating y of r. Then step 3 involves computing the output by involving all the training patterns, and finally compute the robust objective function by computing the value of the robust objective function of the network and storing it. Then step 5, if I is a multiple of T, capital T, adjust the size of the network and confidence interval of the residuals based on the following procedure. If norm or the magnitude of the discrepancy between ER of I and ES is greater than the upper entropy residual or the amount that we mention it as a threshold value delta, then the objective function changes rapidly, reducing the confidence interval by finding new cutoff points, that is given by sigma nu equal to sigma volt into RD if sigma greater than sigma L or sigma volt itself if otherwise, where RD is the decreasing rate and sigma L is the lower bound of the confidence interval of residuals. If the norm between the discrepancy of E r of I and E s is greater than the upper threshold, the objective function does not change rapidly, then add a new node to the network by the adaptive growing technique with a memory cube. Then check the outgoing weight of each node and remove these nodes with outgoing weights smaller than the prescribed threshold, because they do not have any significance in the performance of the training of the network. Then store the current objective function E r of I to E s. Step 6, if E r of I less than sigma stop, that is stopping threshold, then terminate the learning procedure, otherwise repeat by continuing to step 7. Step 7 is update the parameters of the network and continue with the iteration from step 3 onwards. Now, this is one of the simulation results that shows how the function approximation has been done with the M estimation. That is the original data, and the RBFN approximation is given by the red profile. Now, coming to the second part of today's lecture, which is robust control of a single link manipulator using radial basis function network. Now, we know that the dynamic model of a general n degrees of freedom robotic system is given by tau equal to m of y y double dot plus c of y comma y dot into y dot plus g of y, which means that m of y is the inertial matrix of size dimension of size n cross n, which is a function of y, and the Coriolis matrix, which is C of y comma y dot, which is a function of both y and y dot, is called a Coriolis and centrifugal matrix, and G of y is a gravity vector of size n cross 1, which depends on y, and tau is the joint torque vector of size n cross 1. In many practical purposes, m of y, c of y comma y dot and g of y, these are the network parameters which are unknown to us. In order to eliminate this problem, we use an radial basis function network to model these network parameter matrices m of y, c of y comma y dot and g of y. If m of y, c of y comma y dot and g of y are the ideal values of the respective matrices, that is the actual values of these matrices, and m SSN of y, c SSN of y comma y dot and g SSN of y are the outputs of the ideal radial basis function networks, then we can write the following equation, which is the ideal values m of y, c of y comma y dot and g of y, and the ideal radial basis function outputs m SSN of y, c SSN of y comma y dot and g SSN of y by this relationship, which is my equal to m SSN of y plus em. Similarly, c of y comma y dot equal to c SSN of SNN of y comma y dot plus EC. Similarly, g of y equal to g associated with the ideal radial basis function plus EG. So, EM, EG and EC are the modeling errors of m of y, c of y comma y dot and g of y. So, these are the modeling errors associated with m of y and m s n n of y. That means, the ideal values associated with the model and as well as the ideal network outputs values. That means, the discrepancy between the ideal values of the model as well as the ideal values of the ideal radial basis function network output. Now, we can write the output of ideal radial basis function networks as follows. that is m SSN SNN of y equal to W m transpose multiplied by the activation function output, that is the case. Because of this multiplication that is W transpose into output of the hidden layer, which is psi m of y, where y is the input to the network. Likewise, the ideal output of another network that gives C S N N of y comma y dot being the weight vector W C transpose multiplied by the output of the sigmoidal function, that is psi C of y comma y dot. Likewise, G S N N of y from another network is given by W G transpose multiplied by function output. On substituting the above equations in the dynamic model, we get m of y r double dot plus c of y comma y dot into y r dot plus g of y equal to, where m s n n of y is the ideal value into y r double dot plus c s n n of y comma y dot is the ideal value of the network 2 and the ideal value of network 3 plus E, which is given further by W m transpose multiplied by psi m of y into y r double dot plus W c transpose into psi c of y comma y dot into y r dot plus W g transpose, that is related to the gravity term, that weight matrix associated with the gravity term of the manipulator dynamic model associated with a neural network, and the output psi g of y, that is the hidden layer output of the neural network associated with the gravity term, plus E. Here E is given by E m into y r double dot plus E c into y r dot plus E g. Obviously, the radial basis network function network is, in practice they are not ideal, and hence we can only estimate the values of m s n n of y, c s n n of y comma y dot and g s n n of y. Instead of these ideal values, we are going to estimate them. So, the estimation can be represented by a hat. M hat s n n of y is given by W m hat of transpose multiplied by the output of the hidden layer. Likewise, for C s n n hat and G s n n hat can be obtained from the network parameters W hats respectively. Here W m hat, W c hat and W g hat are the estimates of the ideal values W m, W c and W g respectively. Now, the controller design here is, first let us define the error terms E of t, which is given by the discrepancy between the desired output and the network output, and y r dot is given by defining a term y r dot, which is given by r of t plus y dot of t, where r is nothing but the filtered error of the tracking error E. Okay. So, y r double dot from this second equation is given by r dot of t plus y double dot of t. Now, defining r, that is a filtered error given in terms of the tracking error, that is given by r equal to E dot plus lambda E, we have r y r dot expression becomes y d dot plus lambda E. Likewise, y r double dot is equal to y d double dot plus lambda E dot. Now, we propose the following controller, that is given by tau equal to tau m plus k p into r plus k integral r dt plus tau r. Here tau m is the model estimated control law, that is given by tau m equal to m s n n of y into y r double dot plus c s n n of y comma y dot into y r dot plus g s n n of y. and tau r is the robust term in the control law, that is designed as tau r equal to k or signum of r. Now, to find the adaptive law for updating the weights of the networks, we have to perform the Lyapunov stability analysis of the control law proposed, which leads to the following update law, that is W hat dot for mk equal to gamma mk into sigma xi mk of y into yr double dot into rk. Likewise, we have the update law for weight of Ck and weight of Gk, that is gravity term, Coriolis term and the inertia terms. So, we have these three update laws associated. Here gamma mk, gamma Ck and gamma Gk are the learning rates associated for the respective RBF networks. Now, we have with this control design, we have performed a simulation of a simple single link manipulator whose dynamic model is given by tau equal to m of y, y double dot plus c of y comma y dot into y dot plus g of y. Let m be 0.1 plus 0.06 times sine of y and c be 3 times y dot plus 3 cos of y and g being mgl cos of y, with m equal to 0.02, L equal to 0.05 and G equal to 9.8. Here the initial states are y of 0 equal to 0.15, y dot of 0 equal to 0, and let the desired trajectory be a sine trajectory. Here we propose a network, RBFN network with 2 inputs y and y dot, and there are 7 hidden neurons and 1 output, with the input being y and y dot as I mentioned. The parameters of the Gaussian functions Ci and Bi are designed as minus 1.5, minus 1.0, minus 0.50 up to 1.5 and 20 respectively. These are the centers and this is the bias value. The weight, the initial weight values are chosen to be 0. It can be chosen sometimes random values as well, but in this simulation we have chosen 0. We use the control law that is proposed and the adaptive law with the following parameters: Kr being 5 into 10 power minus 4, Kp being 0.1, Ki being 1 into 10 power minus 3 and lambda being 0.8, and the learning rates being gamma m is 5 into 10 power minus 3, again gamma c being the same value with gamma g being 5 into 10 power minus 3. With this we could get the desired trajectory tracked by the single link manipulator to track the desired sine wave, that is joint angle from the network Q and desired joint angle is given by sine of t. That is a position trajectory. Also we checked the velocity trajectory, that is coming out to be tracking successfully, and then the control input to track the desired sine trajectory is also given in the form of a sine, which is varying with respect to the time, and then the estimated values of ideal values of the network parameters, which are nothing but the dynamic model parameters, which are m, mass matrix or inertia matrix, Coriolis and centrifugal matrix C, and the gravity vector are shown here, with the blue line being the ideal value and m or the red line being the estimated values from the network. Okay. And here we could observe severe discrepancy between the ideal network values and the estimated network values associated with the dynamic model of the manipulator, and this is because the desired trajectory lacks persistent excitation, which is a common bottleneck in practical applications. With this I conclude today's lecture that we have seen robust radial basis function towards function approximation and towards control of a single link robot manipulator. With this, I finish today's lecture on robust radial basis function neural network. Thank you so much for your time.